Hey there, this is Mrs. Steele again. We're going to continue with part 2 of our lesson 2.15 regarding periodic trends. If you haven't watched part 1 of the video, I highly recommend that you begin with that one before watching this one. Our summary from the first video is that regarding effective nuclear charge typically increases when we're looking at a periodic table. If we look at the elements that are all in the same period, which is a horizontal row on the periodic table, the effective nuclear charge typically increases because the number of protons in each of those subsequent atoms is increasing. So there's a kind of a direct relationship there. Effective nuclear charge increases from left to right as the number of protons available in the nucleus increases. However, when looking at the column or the vertical groups on the periodic table, we notice that there's generally an increase in distance from the nucleus to the valence electrons. And the reason why there's an increase in distance is because those valence electrons are located on energy levels that are higher in value. Or another way of saying that is the outermost occupied energy level that has electrons is farther away from the nucleus. Therefore, the attraction between the nucleus and the valence electrons will be weaker if the valence electrons are farther distance away. In addition, there will be more electron-electron repulsion because of the core electrons, which are on the inner energy levels between the nucleus and the valence electrons. Some people refer to that concept as shielding, but I'll go ahead and warn you right now that for AP purposes, I really want you to avoid that term shielding and simply describe the proton and electron attractions as well as the electron-electron repulsions that occur. So to put it simply, effective nuclear charge is not going to be a major game changer when we're looking at elements that are in the same group. Rather, the strength of Coulombic attractions will be most affected by the location of the valence electrons and their farther distance, or the greater number of occupied energy levels as you move down a group. Let's move on. So in today's video, we're going to continue with looking at specific periodic trends. Our first trend is atomic radius. On your fill-in-the-blank note-taking guide, please find this graphic. It shows two atoms side by side. Now, you've heard of a radius in math class, and the radius is from the center of the circle to the farthest outermost, end of that circle. Well, it's kind of hard to measure that with an atom, and you know the reason why? Those electrons are always in motion, so it's kind of hard to get your measuring tape out and measure those electrons. But because by the time you try to measure where they are, they're gone. They've moved to another location. So the way scientists actually do this is they can actually pretty confidently identify the location of the nucleus, or I should say nuclei, if there's more than one, of two atoms that are side by side. And we can just use a little logic here that if you can measure from nucleus to nucleus, that would be double the distance of the radius. So by definition, the atomic radius is half the distance between two nuclei that are side by side. And that's literally how it's measured. Now look here and see if you can notice a trend. When you're looking down a group, what do you notice about the atomic radius? Looks like it increases going down. Look and see if you can understand also what's happening going across the period. Looks like it's getting smaller going from left to right. Well, that's weird. I thought there were more protons. I think there's a little more to our story here. So apparently, let's go to our trend summary sheet. We have our definition of atomic radius. Please make sure you highlight that. It's half the distance between the nuclei. of two atoms. But let's go to our trend section. The overall trend as you move from left to right is that the atomic radius of the atoms tends to decrease. Why does it tend to increase going to the left, or if I say it in reverse, it tends to decrease going to the right? Well, the reason has to do with effective nuclear charge. Okay. Remember, as you go from left to right, the number of protons is increasing. Therefore, the effective nuclear charge is also increasing, which means that there will be a stronger attraction for the valence electrons, or I should say of the nucleus, for the valence electrons. That's what this VE means, valence electrons. Therefore, the distance between the nucleus and valence electrons is going to go down. Okay. Now let's look at a trend. If we look back at this right here, I noticed that the atomic radius tends to increase going down a group. So let me write that in. The trend is that the radius tends to increase going down a group, and draw a little arrow here on my little simple periodic table template so I can see the trend. Well, sure, the number of protons is changing, but that's not really the reason why. The bigger reason why has to do with the fact that the valence electrons are located on a higher energy level which is a farther distance from the nucleus. So there's weaker Coulombic attractions between the protons in the nucleus and the valence electrons. And there's also greater electron-electron repulsion between the core electrons, which are on the inner energy levels, and the valence electrons. So what does that do? It creates a larger atom, or an atom. Maybe I should clarify that. When I mean a larger atom, I mean an atom with a larger radius. Okay? There you go. Let's go to another trend, ionization energy. Ionization energy means the energy that's needed to remove an electron from a neutral atom. The energy that's required to strip away an electron. Look at the picture here over on the right of this Bohr atom. It has 2 electrons on the first energy level, here and here. It has 8 electrons on the second energy level, and it has 4 electrons on the third energy level. So if I look at my periodic table, I'll go, oh, this is silicon. Got it. Well, essentially what this is saying is there's a certain amount of energy that it takes to rip this electron away. This takes energy to remove this electron. Okay. We term that energy ionization energy. So I would underline that word energy and then say remove an electron. What seems to be the trend? Well, let's look at our little graphic here and see if we can find one. This can be a little bit trickier, but we can find it. Let's pick a group that we're familiar with. How about the noble gases? That's group 18. Helium, neon, argon, krypton, xenon, radon. Do you see a trend as you move from each noble gas? I do. I notice that the ionization energy is going down. So we could say that the trend is that it typically, it decreases down a group. Another way of saying that is that the ionization energy increases going up a group. Well, how come? Well, once again, it has to do with the positioning of the valence electrons, their distance from the nucleus. As the distance between the nucleus and valence electrons increases, this creates weaker Coulombic attractions between the protons and the valence electrons. Therefore, it takes less energy to remove a valence electron. And that's the definition of ionization energy. Let's look at the trend as we go from left to right. This one we've got to be a little more careful of. So each of these data points here, I'm going to start with not helium, but lithium, which is down here. That's period 2. And as I work my way, there are a few little zigzags here, but I see an overall positive line heading all the way across the period from lithium to neon. So I can arguably say that ionization energy typically increases across the periodic table. Well, what's the deal with that? Why do we see an increase going from left to right? Well, I think there has to do with that effective nuclear charge concept again. Across the period, from left to right, the number of protons in the nucleus is going up. It's increasing. Therefore, the effective nuclear charge, or in other words, the pull or attraction of the nucleus on those valence electrons, also goes up. In conclusion, it will take more energy to overcome those Coulombic attractions. Between the protons and the valence electrons, like so. All right, so that's ionization energy. Now, take a moment and I'd like you to complete checkpoint question number 1. Pause the video. I hope you attempted each question below. I'm now going to show the answers, but without giving an explanation. Please consult your teacher if you still have questions. Number 1, rank the elements in each set from greatest to smallest atomic radius. Lithium will be the smallest, then nitrogen, then fluorine. Question B, lithium will be the largest, then nitrogen, then fluorine. Next, for B, iodine will be the largest atomic radius, followed by bromine and then chlorine. Finally, for part C, silicon will be the largest atomic radius, followed by phosphorus, nitrogen, and fluorine. Part 2, put these in order from lowest to highest ionization energy. Strontium will have the lowest ionization energy, followed by calcium, magnesium, beryllium. For the next, it actually is already in order: boron, oxygen, and fluorine. And lastly, it would be rubidium, iron, phosphorus, and chlorine.